Hi, everybody. My name is Olufemi Odegbile. You can just call me Femi. I'm currently a PhD candidate at University of Florida. My advisor is Shigang Chen. I'll be graduating in August and assuming a position as assistant professor at Clark University. Yeah, my uh, my topic is hierarchical virtual bitmap for spread estimation. Sorry about that, and traffic measurement. So let's start. This is the outline of my paper. The presentation. I will start with background and problem statement. Then I will move to how we design the sketch, which is the main topic of the paper. I will discuss the evaluation, and I will conclude and talk about our future works or future direction. So now to start with, I will talk about background and problem statement. Now, network traffic measurement is essential to network management. For example, where network traffic measurement is essential in access control, uh, also in accounting and billing, in network policy enforcement, in network security, load balancing to relieve congestion in the network, and so on and so forth. Now, because of the direction of this paper, I will first of all make this define some terms. I'll be talking a lot about flow. So what is a flow? A flow is a collection of elements with a common identifier. As an example, we could say that a flow is a set of all packets from a source IP address. So for example, in a data center, we can say, if you have a specific IP address for a server, we can say all the packets sent to that server in a particular period of time, maybe over 1 minute, in a day, in a month, in a year, we can say all those packets are flows. And you know that there may be a lot of source addresses that is contacting a particular server. So all those packets, we can identify them as a flow. No, that is an example. I should say that flow is not really restricted to computer networks alone. So it's applicable to all of its other domains. So, but for the purpose of this research, we focus on computer networks. Now, there are two fundamental problems when we are talking about network traffic measurement. When I say fundamental, there are also many more problems that we can divide, but the fundamental problem is, how do we calculate the size of a flow? And the definition of a size is total number of elements. In case of the example that I gave before, in that case, the flow size can be the total number of packets from a source to an IP addresses. Now, the second fundamental problem is flow spread measurement. It means that the number of unique elements. Now, in the first problem, size is all the elements. In the second problem, we are dealing with unique elements. Now, an example of that is the number of unique source IP, number of unique destination IP that contact a source IP, or number of unique source IP addresses that is communicating with a particular destination address. So now, in this paper, we focus more on spread estimation. So going forward, I will only be talking about spread estimation. Now, so let's review the related works of prior art. In general, in the literature, the way to efficiently measure spread, there's been a lot of sketches. We call them sketches. They have been proposed to measure flow spread. And what do you mean by sketches? Sketches are just compact data structure. They are small. We can install them on switches, and we can record the whether size or whether spread that we want. And without, we should know that in data center switches that they receive millions of packets in an hour. We don't want to implement a traffic measurement algorithm or sketches that will slow down the high-speed network. So that is why it is very, very important that sketches are compact so that they will not disrupt or they will not impede or slow down the flow of the network in data center or high network activities. I'm using data center as an example. Now, so what are the, let me give some example of sketches that we have in the literature. There are some sketches that target single flows. They can measure the spread of a single flow. For example, we have what we call bitmaps. We have FM sketches or hyperlog law. There are a lot of them, but I'm only focusing on this now. Now, another area of research is in a single flow, but in a computer network, we may have thousands of flow, millions of flow in 1 hour. We don't have enough resources to create sketches for each of the flow. So another research area is, what about if can we measure all the flows together using the same common resources, that shared resources? So there are a lot of sketches in that area, which is virtual bitmaps. I developed in my group here, our computer network group in University of Florida. Open Sketch, Bitmap, C-Sketch, or V-Sketch, a lot of them. Now, there are other sketches also, we call them multitask sketches. What that means is that I want you to understand that I'm only talking about a specific task, which is spread estimation. Now, there are other tasks, as I said before, which is size estimation or flow distribution. That's another task. Or hierarchical flow measurement, that's another task. There are some sketches that are designed to do more than one task. Now, depending on the kind of activities you want to be involved in, you can choose single flow sketch, you can choose multi-flow sketch, or you can choose multitask sketch. Now, in this work, I want you to understand that these sketches are only designed for single level flow spread estimation. I will define what I mean by that in the next slides. So let me give an example. As I said, all the flows, all the sketches I mentioned so far, they make a specific assumption. The assumption is that the flows they are measuring, they are disjoint. What I mean by that is that they have no elements in common. And because I'm talking about computer networks, they have no packets in common. So what does that, consequently, each packet that arrives will be recorded exactly once for the flow that it belongs to. But because of that, we can run into a problem with a type of flow that we call hierarchical flows. These are flows that are not disjoint. They are nested in each other. I'm going to give the definition, formal definition of hierarchical flows later. Now, so going forward, I will focus more on hierarchical flow. So in the next slide, I'm going to give a flow model of what are the flows I'm talking about, that the current state of the art or current approaches in the literature are not best suited to address that kind of flow. So let me give a definition of hierarchical flows. Hierarchical flows, as you see here, they are nested flows. That is, we have level. In this example, we have L levels. The first level is a parent flow for all the other flows in all the other levels. For example, F2 is a child flow of F1, while F1 is a parent flow of F2. F2, any packet that belongs to F2 belongs also to F1. That continues until we get to the base flow. The base flow is at level L. So, and with that, any packet that belongs to base flow FL also belongs to FL minus 1, belongs up to F2 and F1. So that means that these flows are not disjoint. And what I'm going to give an example about that now, a concrete example to illustrate this. Now, suppose in a data center or in a network, I have a router or top level or top of the rack switch. The switch connects stub networks. And in each stub network, I have sub networks. Now, each subnetwork contains individual machines. Now, let me define three types of flows. The first flow means that the traffic from a stub network to another stub network. The second example of a flow is a traffic from a subnet to another subnet, either in its own subnet or to another subnet in an external subnet, stub network. Now, this third type of flow, suppose it is the flow between individual machines. Now, obviously, these three flows are nested in each other. Wow. Any flows that belongs to an individual machine also belongs to this subnet, and it belongs to this stub network. So these are not the disjoint flows. So consequently, if a packet belongs to F1, F3, which is our base flow, and I want to record or process the packet and record the spread, I will have to record the spread for F3, record the spread for F2, and record the spread for F1 separately. That is 3 times. So if I do that for every packet that comes in, that means that I'm processing each packet 3 times. And if I have 100 packets, I'm going to be processing it 300 times. This degrades the network throughput. We don't want that. We only want to process a packet once. And once we process a packet once, we'll be able to process it for all the flows that it belongs to. So that is the problem. So let me now talk about the problem statement. I've already mentioned it. The problem statement is that we want to design a sketch, name sketch, that if a packet comes in that belongs to an hierarchical flows, we don't want to process the packet for each of the hierarchical flows. We want to design a sketch that by processing the packet once, we would have processed the packet for this flow up to flow F1. So that is what this paper is all about. Now, that goes to the second section of this presentation, which is how do we design such a sketch? Now, the name of this sketch is Hierarchical Virtual Bitmap Estimator. Going forward, when I say HVE, I mean Hierarchical Virtual Bitmap Estimator. Now, for the purpose of our discussion, let's still assume that we are dealing with F1, F2, FL, and they are all hierarchical flows. I've already defined what an hierarchical flows are. Now, first of all, what we need to discuss is that how do we design a virtual array to store the spread? I'm going to be talking about that. And the next step is how do we record the spread? And once the spread are recorded on the switch, how do we query the array to retrieve the spread of individual flows? Now, let's start by, first of all, I discuss about not everybody understands the concept of counters. If you want to count something on a switch, or for example, there is a utility designed by Cisco, which is NetFlow. NetFlow uses counters to record the size of a flow. But we cannot use counter for spread, because spread, we need to remember whether we have seen an element before or not. So because of that, we need to for our own work here, we want to design a container to record the spread of hierarchical flow. So to do that, we make use of what we call virtual arrays. Let me give the definition. Now, we start by having a physical array B of n bits. There are n bits. The next step is F1, which is the parent flow, topmost level flow. We select at random X1 bit. Of course, X1 is less than M from B. And it will form its own, what we call virtual array. So all the elements that belongs to F1 we are going to record the spread in BF1. Now, remember, all these flows, they are hierarchical flows. We want to exploit the hierarchical structure of the flow. So that is the way we did, that is how we design our virtual array too. So in this case, S2 will select its own virtual array from, not from B, from BF1. So to form its own virtual array. We continue this process. In general, let me give a generic term for that. With Sj, that is flow at level J. And just to remind us that level J flow is a child flow of level J minus 1. So with that, that means that the virtual array of Sj minus 1 is bigger than the virtual array of Sj. So Fj we select Fj we select at random Sj minus Sj bit from virtual array of Fj minus 1 to form its own virtual array. And this is the way we do it for all the flows in an hierarchy. Now, just to give you the visual representation of what I just explained now. So we start with physical array, physical bit of M bits. This is a physical array, B. Now, flow F1 will select its own bit at random from this physical bit to form its own virtual array. Now, Fj minus 1, now I didn't write F2. F2 will select its own bit from the virtual array of F1. Now, suppose we have Fj minus 1. Now, Fj will select its own bit from Fj minus 1. So you can see from the picture representation, we've explored the structure, hierarchical structure of the flows to also build a hierarchical virtual bit array. The next step is to talk about, now that we have virtual bit array, how do we now record the spread of each flow? Now, to do that, when a packet comes in, and that packet belongs to F1, F2, FL, this is done on the switch. The switch we choose will start from BFL. That is the base flow, the lower level flow. In this case, FL. It will start from its own virtual array and select a bit at random from this virtual array and turn it to 1. But remember, the way we construct BFL is selecting bit from BFL minus 1. So this is the relationship. So a bit here is equivalent to this bit in BFL minus 1. We can continue this process until we get to the physical bit in B. So we want to flip this bit. However, this bit is equivalent to this bit in the physical array, the way because of our construction. Now we flip this to be equals to 1. Now, in our design, in our evaluation, we use pipelining to do this computation so that we do it in 1 clock cycle. So in our hardware implementation. Now, so after we flip this, so this is the recording part of it. After all the flows are recorded, the next thing is for this bit array will now be exported. It depends on the architect of the network. If the network is a distributed network, it can write this B, physical array B, to disk, or we can export this B to a controller if it is a centralized network like SDN. So the next step is that if we now want to estimate a spread of any flow F1 to FL, how do we estimate that? That's why we propose this theorem, and we prove this theorem that if we have a hierarchical flow Fi, I from 1 to J, and we want to estimate the flow, the spread of Fi, after we have finished the recording and we want to do it offline. So then the estimator for HVE is this equation. Remember, I introduced another terms which I define as VFO, which is the number of 0 bit in the physical bit, and VFGI is the number of the proportion, not the number, the proportion of 0 bit in each virtual array. So now, when j is equals to 1, this is a special case, and we can prove that this is similar to a very accurate first level spread estimator, which is virtual bitmap, one of the prior arts that I'm comparing my work with. So this paper actually generalizes virtual bitmap. Virtual bitmap is at this level is single level estimator, but we have been able to generalize this virtual bitmap to become a hierarchical level estimator. That's our HVE. So this theorem, if you are interested in the proof of this theorem, is in the paper, and you can get my email in the paper too. If you have any question about this theorem, I will be able to communicate with you through email. So now, the next thing that we want to talk about is evaluation. How do we evaluate our estimator? Now, what the flow information that we need, we use, we downloaded the real internet traces from CADA to stimulate a 2-level hierarchical traffic model. Now, the second level flow consists of the packet to a destination address. Actual spread of the second level flows ranges from 1 to 5,000 spread. Now, for the first level flow, which is the aggregate flow, we'll use the 16-bit private of the destination address to determine the second level, first level flow. Now, actual spread of this aggregate flow, which is the same thing as first level flow, ranges from 1 to 15,000. Now, what are the prior arts that we compare our work with? As I said before, this virtual bitmap is one of the most accurate first one level spread estimator that we have. And this is the virtual bitmap that we actually generalizes in our work. So we compare our work with this. And also we use OpenSketch is a popular paper, but we use an OpenSketch in the sense that we introduce a bitmap in it. So OpenSketch is, this is just like if you are familiar with CantMe, but instead of using a Canton and CantMe, we replace it with a bitmap. So now, the next thing is that how do we? There are two approaches that we follow here in our prior art. What we do is that we encode all the flow, whether first level or second level flow, in a single memory. And so that is the first approach that we did. The second approach is we divide the physical memory into two. We record all the first level flow in half of the physical memory, and we record the all the second level flow. We record them in the other half of the physical memory. So this I denote it with an asterisk. So when I implement virtual bitmap, if I implement it for the first approach, I only use virtual bitmap. Now, if I implement virtual bitmap for the second approach, I put an asterisk with it. Okay, when I showed you the chart, that is what it means. Now, what are the metrics that I follow? Now, remember the main purpose of this paper is to make sure that we are not doing unnecessary computation. We only want to process only the packet only one time. So that means that we need to check whether we have been able to increase the throughput with our design compared to the prior art. So what do you mean by throughput? Which throughput indicates the processing speed of the three estimators, that is HVE, which is the one that we introduced, virtual bitmap, the second one, and OpenSketch. So we want to see whether we have been able to increase the throughput but with our design compared to the prior art. Now, the next one we want to do is that, since we are improving the throughput in our estimator, are we doing that at the expense of the accuracy? Now, because we are processing one packet for for multiple flow, are we compromising the accuracy of our estimator? That is how I want to also check the accuracy of our estimator. That good if we achieve high throughput, but do we degrade the accuracy of the estimator? We want to check for that. Now, so let me present the result. The first result I'm going to present is about the throughput itself. Now, we carry out two implementation. One is software implementation, in which we use Java to implement it on a CPU. We use mini workstation to do this because of large data that we work with. Now, we also implement our design also in the GPU. So what the first thing we do is that we look at how many packets can we process, how many millions of packets can we process per second. So for our HVE, during the, of course, the software implementation is slower than the GPU implementation. We were able to process more than 4 million packets. This one, 696 million packets. As you see, compared to the estimators, prior art, we outperform all of them in terms of the throughput, which is what we expect. And you can see that for the GPU implementation, so we also outperform even the most accurate spread estimator in the literature. We outperform it. Now, the next thing is to check whether do we compromise the accuracy with this kind of improvement with our throughput. So we check. So now there are two ways that we evaluate the accuracy. After we encode all the information, then we check, we estimate the spread of all the first level flows, and we plot them in a graph. So we compare this line on the x-axis is the actual spread of the flow. On the y-axis, we have estimated spread. We also plot y equals to x line to see whether how accurate our estimator is. Now, in this case, if the closer the point, each point represents a flow. The closer the point is to this line, to this red line, tell us how accurate our estimator is. And you can see that in our estimator, almost all the points clustered around the y equals x line. So this gives us the impression that the first level flows spread is accurate. Now let's compare it to the other prior art. For OpenSketch, ours perform better than it. And for OpenSketch, for two approaches that I mentioned before, our estimator perform better than it. Now let's compare it to one of the most accurate spread, which is virtual bitmap. Now you can see that for large flows, for first level flow, our HVE still outperform it. The main reason is that both large flow, which come from the aggregate flow, and smaller flow, which come from the second level flow, they are occupying the same. The large flow introduces more noise to the low level flow. So that is why ours is much more accurate than that. Now, next thing is to now see what about the second level flow? Do we still see this level of accuracy with our work? So let us look at it now. For the OpenSketch, ours, you can see the points are still clustered around the y equals to x line for second level flows. Ours is still better than OpenSketch, as you can see. Now let's look at for the virtual bitmap. We can't say definitely, we cannot say definitely that our own is better, but it's comparable, and that is what we want. So we want a comparable, comparably accurate estimator to the state of the art, while we deliver much more improved throughput. That is what we want, and that is what we see in our results here. And I have more results, numerical results in my paper. So if you want to look at it more, and I'm happy to discuss more about it. So what are the conclusions? The conclusion, this paper proposes a new hierarchical measurement architecture, HVE, that's our estimator, that extend the capability of existing single level network traffic measurement tools and enables more efficient online data encoding of flows with hierarchical structure. So now we've showed that our hierarchical virtual bitmap estimator throughput significantly exceed prior art, while its accuracy is in general comparable to the prior art. Now, for the future world, the extension to this paper, I'm going to focus more on the mathematical analysis of our HVE. I don't have enough space in this paper now. We'll be looking at what is the biasness? When I say biasness of our estimator, that is as the expected value of mean of our estimator is equals to the actual spread. So that is what I'll be doing rigorously, analyzing our estimator. Also, we are going to be developing the confidence interval for this estimator. It's also part of the accuracy of it. And the main reason we want to do that is that we want to improve the accuracy of HVE by true differentiated memory allocation. Now, in this paper, we assume that all the flows are the same level. They use the same number of bits. That is, the size of the virtual bitmap, a virtual array of all the flows at the same level, they are the same. Now, that means that we are using the same size for small flow and large flow. That is not very good. And we're going to be demonstrating why that is not good. And we're going to be introducing another concept. What about if we dynamically allocate the number of bits that we assign to each flow? Can we improve the accuracy of our estimator through that approach? Those are the things we are going to be exploring with the extension of this paper. Thank you very much. Any question?